A very warm welcome to this video about the directional derivative of a function in two variables. So we know that the directional derivative of a given function f according to a given direction v at a specific point x0, y0 is the gradient of the function f at this position dot product with this given direction v. The given direction v is now here in 2 dimensions. That indicates the direction of the derivative we are interested in. And in addition, we have the assumption that this direction is a unit vector. So if it is not a unit vector given, you have to normalize it. I would say we look at an example using these formulas down here. So I need the space up here for further derivations later on. So the two-dimensional function, which is given x times y squared plus 2xy. The specific point is 2, 1, and we are interested in the slope in the direction of northwest, so in the northwest direction. Let's look at a sketch. We start sketching the x and the y coordinate axis, and our point of interest with the coordinates 2, 1 is here. And northwest means you go one step to north and one step to west. So -1 in x and +1 in y. So what you have to assume is in this two-dimensional plane here, that you assume it as a topographic map of a mountain landscape, for example. And you are looking from the top, so the top view, and you are standing at this position, 2, 1. And you move northwest. And we are asking, how steep is the slope, uphill or downhill in that direction? Usually what you are interested in when you're standing at this xy coordinate, what is your actual height? So the elevation, and you get it from this formula. So let's call it Z0, which is then f evaluated at 2, 1. So 2 times 1 squared is 2 plus 2 times 2. So we have altogether 2 plus 4 is 6. So this is simply the function value at our point of interest. So the height we are standing here is 6. So we use the formula from above. What we need first is this direction, and the direction we model here as -1 in x and 1 to the y direction. You have to normalize it, so you divide by the magnitude of this vector, so which is the root of 2. And now we also compute the gradient. We also need the gradient in the formula. So gradient of f at this point of interest, which I neglect here. So what is the gradient of this function f? You derive according to x, which is y squared plus 2y. And you derive according to y in the second component. So 2xy plus 2x. These two partial derivatives have to be evaluated at the point of interest, at the specific point 2, 1. And we get for the gradient, if you plug in for x is 2 and for y is 1, y is 1 squared plus 2 times 2 gives 3. 2 times 2 times 1 is 4 plus 2 times 2 plus 4 is 8. Okay. We will show later on that the gradient points in the direction of the steepest ascent. So 3, 8. But we are here interested in this directional derivative, so in the slope in the direction of northwest. So the k is the directional derivative at the point 2, 1. And according to the formula above, we have the gradient, which is 3, 8 dot product with the direction, the northwest direction, v. So what you can do here in the dot product, this prefactor can be pulled out, so it can be taken out to the front. I would not include it in the vector, so we write 1 over root 2. And now compute the dot product. 3 times minus 1 is minus 3, plus 8 times 1, so 8 minus 3 is 5. 5 divided by root 2, and if you use the calculator, this is approximately 3.5. This is quite a large increase. It means if you go in your plane 1 meter to this northwest direction, you go uphill 3.5 meters. So you have to climb. So once again, if you imagine this plot similar to a contour plot or the topographic map of a mountain landscape, it means if you go 1 meter here in this XY, then your elevation, your height raises by 3.5 meters. Next, let's consider the directional derivative and determine for which vectors v this directional derivative is maximal. So we maximize this directional derivative up here. This one. Okay. How to do that? We have to make a short recall from Math 1. So the dot product between two given vectors a and b can also be written as magnitude of a times magnitude of b times the cosine of the enclosed angle. This is actually also the definition of a dot product. So it looks like this when I draw two vectors. So you see here vector a and vector b. They have not necessarily the same length, and here is the enclosed angle. So I use this property here to continue this derivation. So the magnitude of the first vector, which is the gradient, times the magnitude of the v vector times the cosine of our enclosed angle. So we have assumed that this v vector, the direction, is a unit vector, so its magnitude is 1. Here you don't have any variables anymore. It's a fixed number like 3, 8. So the only variable is the angle phi. And you want to maximize this expression over all vectors v. So you'd only change the phi in your in this expression in order to change the vector v. So what does this mean? It means actually the cosine, the enclosed angle of the enclosed angle must be maximal, and the maximal value is 1. And when is the cosine equal to 1? If the angle itself is 0 degrees. So what can we conclude from this? The enclosed angle is 0. It means the gradient points into the same direction as the vector v. Or in other words, that the maximal, the v, which maximizes the slope, is the gradient. So this direction here is not normalized, because if you look here, the gradient is 3,8. It's not a normalized vector here, but I'm only interested in the direction. And this is the direction of the steepest ascent. Let's write it down fully. So direction of steepest, so the highest value, ascent. Ascent means you go above, you go uphill. So for free, you also get the actual slope, because this is only the direction I highlighted here. It's a vector. If you want this maximal slope, you simply take the magnitude of the gradient. So that's all we wanted to show. Once again, if you want to compute the direction of the steepest ascent, you simply compute the gradient and evaluate it at the specific point. And if you want to compute this maximal slope, then just take the magnitude of the gradient. So if you want the steepest descent that you go downwards, then you take minus the gradient. Well, we include these observations here now in our example. So what is the direction of the steepest ascent here? It is the gradient, so I can directly write here this is Vmax. And if you want the slope Kmax, you simply compute the magnitude of this gradient vector, which is in our case the square root of 9 plus 81, 64 plus 9, sorry, is 73. So we have approximately 8.5. So let's look to the sketch. So the gradient vector means 3 dots, 3 units to the right and 8 upwards. So it looks approximately like this. And our Kmax is much higher than these 3.5. It's approximately 8.5. So if you go 1 meter in this direction, your elevation raises by 8.5 meters. If you consider the opposite, the reverse vector, then for sure you go downwards. So this is the direction of the steepest descent, which is then minus 8.5. Imagine you are hiking and then this should be clear. So in addition, now we want to consider in which direction you should walk here if you want it easy. So not a climb, but a flat path along a contour line. In other words, you want to find the direction of v where the directional derivative is 0. So additional task here, I use fancy colors. We want to know when is the directional derivative, which is defined via this formula, equals 0. So when is the directional derivative, its slope, equal to 0? So what does this mean? This is 0. This dot product is 0 if the vectors are perpendicular. So this means if the vector v is perpendicular to the gradient. And we sketch this result. So you see here in 2D we have two possibilities. The first one is here, that the slope is 0, and the second one is the reverse vector. So if you are standing here, if you go into this direction of the gradient, you go uphill. So the fastest path to raise the height. In the reverse direction, you go downwards. And if you go here perpendicularly to these two red vectors, then you don't change the height and you stay on a flat path. So once again, we compare the slopes in this graph. If you go in this direction, it's uphill, steepest ascent. Here we have a slope which is between 8.5 and 0, but still positive. So here you always go up. Here there is the flat path along the contour line. In this region, you go downwards. Here is the steepest descent, also downwards. Here again, the flat path along the contour line, and then you increase your height also in this, your height in this area. Thanks so much for your attention, and see you in the next video.